But in order to further understand how memory problems develop and what results in memory problems on a synaptic level, we wanted to determine, does learning cause LTP-like changes in the strength and structure of the synapses in order to show?
Actually, before you jump, did you test your NMDA receptor blocker with mice as well and see how they compare to the HD model?
No, we didn't. That would be a really good experiment to block LTP links. So we wanted to find out, does learning cause LTP-like changes in the strength and structure of the synapses following unsupervised learning? But what do I mean by LTP-like changes in LTP? LTP isn't it reduced by theta burst stimulation in brain slices or rats? It produces an immediate and prolonged increase in synaptic strength and structure. Currently is the best model for high capacity learning memory because it fits the stringent criteria for memory formation by being very synapse specific. Numerous lines of evidence suggested that stabilization of LTP depends on multiple signaling cascades linked to active polymerization. As you can see from this diagram, theta burst stimulation results in a specific neurochemical signature of the postsynaptic spine, which includes the phosphorylation of cofilin, which allows the actin to polymerize and produce spine enlargement and the enlargement of postsynaptic density. Studies in our lab by Lu Chen have attempted to quantify these postsynaptic changes that occur following theta burst stimulation. What was found is that theta burst stimulation produced a significant increase in picofilin positive spines. And as you can see, picofilin positive spines are found very rarely in the brain, much rarely than cofilin and KC95. And importantly, they colocalize with KC95, allowing us to measure the synapse size of these potentiated spines. Thus, these studies establish that picofilin KC95 double labeling is a synapse-specific marker for LTP-like changes. Thus, we wanted to use this technique to answer the question, does potentiation effect occur within individual synapses following unsupervised learning? We had 3 groups of rats, exploratory vehicle treated, exploratory CPP treated, which were exposed to unsupervised learning, and the tissue was stained for picofilin and KC95. Control rats were transported to the box but not placed in the enrichment box. We used a confocal microscope to look at a specific region in the CA1 and object analysis software that was developed in our lab to count and measure the area of label structures. The staining of in vivo tissue showed similar results as of hippocampus slices. The phosphorylated cofilin is found much more rarely than total cofilin and the number of PSDs. And importantly, the picofilin and PSD95 were colocalized, allowing us to study this interaction. Quantifying the number of picofilin and label picofilin and PSD95 structures, we find that learning increases the number of spines with a positive picofilin stain by 30% as compared to clone cage controls. And importantly, CPP treatment on these animals completely wiped out this effect. So even though the CPP treated animals explored the environment to the same degree, they did not show these changes in phosphorylated cofilin. Quantifying the number of PSD95, we didn't see any change in the number of PSDs. However, the double labeled PSDs that have both picofilin and PSD95 showed a 35% increase. And importantly, the double labeled spines had much greater synapse area than non-double labeled spines. Thus, these studies show that LTP changes do indeed occur in individual hippocampal synapses during learning. That we used this marker potentiated spines and found that picofilin does increase. Does CPP block this effect? And CPP block this effect by blocking an NMDA receptor. These findings open a way to identify memory traits on the synaptic level, which was previously an elusive goal in neuroscience because of this, because synapse structures are so small and widely distributed. Thus, we used the methods, but we had to significantly update the methods that we used in the previous study and adapt new technology in order to be able to map wide regions of the hippocampus. we used wide field fluorescent microscopy with automated stage in order to scan a large area of the hippocampus. We've identified or selected sample points throughout the hippocampus to include different subregions and photographed the picofilament and PSD95 structures in all these subregions in order to identify the region distribution of the synaptic changes throughout the hippocampus following learning. Previous study that I showed you, only a very small region of the hippocampus was scanned with a focal microscope and quantified. That took a very long time, about 3 months of photographing in order to get these results. So significant changes had to be made in acquisition of the data. And we're able to use this methodology to photograph and accumulate 1,000 sample points from 2 animals from different regions of the hippocampus and quantify the picofilament PSD95 structure. So what we find by analyzing the different sample points is that the only region that produces such an increase in picofilament positive spines is in the CA1. CA2, CA3, and NHRs did not produce a significant increase in picofilament positive spine, suggesting that unsupervised learning produces very original specific synaptic changes. And then we're very lucky that we picked this region for the first study. To further quantify exactly what region of CA1 produces this kind of change, we separated CA1 into the 3 subregions, CA1A, CA1B, and CA1C, and looked at stratum oriens, proximal stratum mediatum, and stratum radiatum distal. So we find specifically that in CA1A proximal and CA1B proximal and distal is where this specific increase in phosphorylated profilament occurs. These studies led us to this kind of sampling technique allowed us to sample from different regions and compare region-specific differences. We also wanted to we also set up a spatial estimation of we wanted to discover the spatial estimation of individual neuronal traces, the traces from each individual animal, and see if perhaps they're different from animal to animal, right? And see if animals that are exposed to the same environment have different patterns of encoding throughout the hippocampus. So this linear sample arrangement was produced as a grid, and software was used to estimate the number of picofilament positive spines between these regions. So what we find, so we produce this heat map, which shows you the density of picofilament positive PSD95 elements, and this shows that this particular animal had really hot region in the C1B that had a lot of synaptic changes. It also had synaptic changes in the areas that you see not as hot, but it included, it shows that as compared to these regions, some synaptic changes did occur in these subregions. So in the conclusion, we've established and validated a novel behavioral task for rodents for testing high capacity learning. It opened a way to study the mice models, rat and mouse models of cognitive dysfunction and test the effects of therapeutics on these models. Demonstrated that changes in spirochemistry as seen with LTP actually occur with high capacity learning of a novel environment in this behavioral paradigm, and that these changes in spirochemistry can be used to mark regions where memory encoding is actually taking place in groups of animals as well as individual animals. So allowing us to study the engrams that are produced as a result of experience to learning. So this is it. I'd like to acknowledge my advisor and collaborating advisor who provided supervision during graduate school. As we know, unsupervised learning doesn't really work. It requires strict supervision and guidance, and I'm really grateful that science and taught me science. I'd like to thank my community members, Mark Smith and Robinson, for also providing really guidance and support throughout several years in the department. And I really like to acknowledge my project collaborators, which Christopher Rex, who set up a lot of the spline counting analysis paradigms that were crucial for all the projects that I was involved in, and he was a really good friend and taught me pretty much all the techniques in the lab that I've been using. Lu Chen for setting up the immunohistochemistry, which was able to identify the LTP-like mechanism in the splines, and setting up the wide field microscopy technique, which allowed us to perform the regional distribution studies. Thank you very much. Danielle Simmons for being there since the very beginning and providing help and support and providing the valuable Huntington's mice that we used in the studies. Linda Palmer for setting up that supervised learning paradigm. He's a visiting professor who introduced the experiment to me. And Nico Kramer for always being there and providing the menopause rats. Undergraduate assistant, Keely, who was helping with the behavioral stuff, and Young, helping with the focal microscopy. The faculty, who has also helped me greatly in graduate school since the very beginning, and provided support and guidance. The family, Monty, the baby boy, about to tell me minutes. Charco, PhD, or Dr. People. My parents, Olga, Oleg, and my brother Alex Fedulov for helping me stay fit and sane in graduate school. And everyone from Gillespie, the anatomy and biology department, who been there from the beginning too, and been really good friends the whole time. So thank you for helping support.
I think a great model, and it's a really nice talk, so congratulations. I'm sure you'll pass it. The question I have is, since you have this great model, using a mouse model, I'm sure that the spines are just about the same size and just as easy to measure. The hippocampus is smaller, it would make your life easier, but the mouse model will also basically generate a lot of data for all these mice, especially these people mice that you have. So, do you think it's easily translatable, or is the mouse and the map very different when it comes to exploration and running?
I think with LTP studies have shown that even though it is much more difficult to stain mouse tissue because of the antibody, we use mouse antibody for P65, so there's some interaction and some tissue differences. I think it is translatable, and actually we have the tissue from the Huntington's mice that we've stained for picofilin P75 in order to identify if the memory problems that the mice encountered in the behavioral test also correlate to deficiency in a phosphorylation of cofilin, this LTP-like mechanism. So I started shooting that tissue, and it looked like it has pretty good staining, but it was kind of started last week, so Dr. Gall told me to drop it and focus on that. It'll get done, yeah. So this is definitely the next step, to apply this technology and study if LTP-like mechanisms are deficient in transgenic mouse models of the disease, and also quantify the regional distribution of these deficiencies, comparing them to mouse.
Very nice talk, Vadim.